Start recording. Well, I hope y'all had a good week off. It's kind of funny. We get a week off and then we come back to school for pretty much 1 week, and then next week is finals, right? So our last official day will technically is next Monday. Um, and of course, it's a non-lab day, so pretty much the way we're gonna do this. This week we're gonna kind of do like a recap, if you will. I would like to go in and talk a little bit about ROC filters, which is the next step. I mean, we've gone through the resonance circuits like in prior to the Thanksgiving break, where we've looked at, and I mean, we've looked at it in the homework. We're at this point, right? The series and parallel resonance. We've done it in the labs. We've had the two labs where we had the series and parallel. We have a formula sheet for both of those now. So we'll go ahead and yeah, I'll do a little recap on the resonance and basically what we're looking at. Excuse me. I mean, ideally, I mean, really, when you think about it, right? Our biggest thing has been throughout this last 8 weeks or 6 weeks, if you will, at this point. Is studying the capacitors and inductors and how they interact, and or I should say more technically is how do they react to frequency. And we've done a few labs and everything, and the homeworks have steered us that way, and how to expect a capacitor to react to frequency and how to expect an inductor to react to frequency, right? And how they interact together when dealing with this. And a slight, let's see here. So, I mean, if we look, right, I mean, pretty much, if it says it right there, if we take a, if we examine like the series resonance formula, but more importantly, not just even the resonance, but just how these three components interact or react together. And if we make our broad statement by the two formulas right here, okay, and by this point, I expect everybody to be somewhat familiar with these two formulas. I mean, at this point, we know that our x of L is equal to 2 pi FL, and we know that our x of C is 1 over 2 pi FC, and how that reacts to frequency, of course, right? And of course, the inductive reactance with frequency is a direct response, and the capacitive reactance is an inverse response. And really, what does that mean in like broad terms, right? So if we were to look at, let's say, inductive reactance per se, as we drive frequency up, we expect the inductive reactance to rise as well. So as a broad statement, we could even say the higher the frequency, the higher the inductive reactance. Now, capacitive reaction is almost like the opposite in a way of that, right? Says we have an inverse relationship. Oh, hold on here. Make sure I get everybody in. There we go. Ah, pardon me. Make sure everybody's getting into the Zoom. Yeah, I had to. Well, one of the ways I do it is it makes you guys go into the waiting room, because in the beginning there I was afraid of there's a lot of talk of the Zoom bombing for meetings and whatnot, and I definitely wanted to avoid that. So I do force you to go into a waiting room, and then you get admitted into the main meeting room, if you will, our virtual meeting room. All right, so there's everybody. So, oh, hold on here. So I mean, ideally, that's what we're looking at. And then if you look at the two statements here, and we can look at this. Yes, this is a series one, but let's take a look at the similarities, right? What's going on here? as far as our parallel. And we have a different setup, of course, but I mean, notice, I mean, really the first statement or the first set of statements here, they parallel. I mean, they are pretty much the same. So when ideally, whenever the X of L or our inductive reactance is greater than our capacitive reactance, we can state, right, that the circuit will be more of an inductive type thing. And then when our capacitive reactance is greater than our inductive reactance, we expect the circuit to be more capacitive. And then generally, what does that do? That sets us up for which way our phase is going to be oriented, right? And that's when we've gone into the resonance where we tried to equal them out. And the main goal there was what? Basically to get rid of that whole phase response, if you will, and try to make the circuit pretend to be all resistive. And it's just a recap. I'm not really going anywhere with this. So at this point, we should, well, by midnight today is the last homework is due, and then the last quiz is due per se, and that is the last I'm assigning. We're just like going to go in and talk about our filters, which is the next step past resonance. And essentially it's looking at how these circuits respond to frequency, or how we could even control their response to frequency. I mean, we've seen in resonance that we can go ahead and control them to the point where we equal them out. So we have what would be called like a balanced circuit, if you will. So we knew what our response would be. We'd have a specific frequency response, and that sets us up to select our components to aid us in this. And then the next step, let me stop sharing that. So I mean, ideally the next step, and we're going to talk about this really, but we're not really going to do a homework with it that our time doesn't allow and whatnot. And I don't want it to get in the way at this point, really. This week, I do have one more lab I'm going to sign out, and it's more of a fun lab, if anything, where we're going to play with some speakers. And we're going to do two types. I do have enough where we do like the little 4-inch speakers. So I do have enough for everybody to have one of those. And then, but the lab also is going to call for a woofer, you know, a larger, like deeper bass type speaker. I don't have enough of those. So what we're going to do, well, we do have 2 days of lab coming up this week. So what I would like to do is have us share, if you will. You know, we'll kind of take turns. So like one set of you will go ahead and work with the smaller speakers and get ahead on that. And then the other set of you will go ahead and use the woofers and then kind of swap. But we have the 2 days to play with it, and we'll go through the lab and do that. And also, I mean, as time allows. So I mean, really ideally this lab should be able to be done in like one lab session, which leaves you with one free lab day. And I mean, essentially, if you do have any labs that you need to be catching up on or be caught up on, that this would be the ideal week for that, as well as any questions you might have that we can go over if you'd like. I mean, both today and Wednesday session. And then on Monday, what I want to do is have us do like a review for the final. I'll do like a Word document list, if you will, you know, main topics to have fresh in your mind. Of course, it's going to be open book, right? So have your formula sheets, you know, even a lot of the stuff is in the Uglies book, believe it or not. You can actually turn to the electronic section, and it does have different RLC circuits in there, and it shows you the formulae for those. Uglies book is so fantastic, and as well as your textbook. I always find the textbook, I mean, unless you have like memorized this thing, it can be difficult to leaf through like a variety of chapters, you know, as many chapters as we've gone through in the last 7 weeks here, right? So, but that's how we're going to be set up. So today, let's go ahead and we'll take a look at filters. I mean, it is the next step with resonance, and And what do we do? What would be a filter? Okay, that's kind of what we're going to be looking at. And essentially, these circuits are meant to be wherever we have a transmitted sign, alternating signal. Doesn't necessarily have to be a sinusoidal as long as we have alternations going. I mean, ideally it is a sinusoidal type waveform, but this can vary. So these circuits can be used in anything where we have signal transmission and not just in communications. This also applies to like power transmission as well, because in power, we're sending a signal from point A to point B and manipulating that as well. And in power, you also want a clean signal. You don't want crosstalk or interference, noise spikes, that type of thing. And that's what you would do with filters. I mean, filters ideally are getting rid of unwanted signals with that would be interfering with your original signal. So you look at the different topics, there's some new concepts, but some of this actually crosses over and go on to your next step where in solid state. So you would have basic solid state and advanced solid state where you actually are manipulating things along this nature, even to the point where we have power supplies, if you will, converting an AC signal to a DC signal. You can use filters for that. In fact, you have, and well, you will see, you would have to use different types of filters in order to achieve a proper DC response from an AC signal. But that's something that you'll get into in the next class set. But this sets you up for that. And ideally, if you have the formula sheets and everything, you should be able to go through that. Then we're just really manipulating. It's the same formulas that we use where we set up what our reactance is. But with filters, what we do is a little more active. We can actually set these up for specific frequency response, if you see here. So if the way we looked at it with resonance, now we did have like a center frequency, right, based upon our component selection and whatnot. And we've seen that there were like a high side and a low side to the frequencies as well, because we don't have like a knife edge response. There's always a rollout, if you will. Well, one step further is that we set it up to have what they call, if you see down here in this graph where it says F sub C, that's the cutoff frequency. And what that would mean is, if you see where it says pass band and stop band, if I were to set up a circuit that responded this way, then what would happen is I would allow all frequencies below my cutoff frequency to go through, and then anything over my cutoff frequency would be blocked. The circuit simply wouldn't do that. Now, if you recall from the resonance circuit, as we stepped up or stepped down past what our ideal frequency response was, the further out you went with the frequency, the lower and lower and lower a voltage magnitude became, right? So on this graph, if you look here, see how they have that A sub B? Well, that is the voltage response. And that's being compared to the frequency response. So what would happen is if we went or tried to go above the cutoff frequency here, it would simply attenuate the voltage down to very much near zero. It probably won't get rid of the signal entirely, if you will, but it dampens it or attenuates it so much that it really has no way of impeding us, getting in our way, interfering with our original signals that we do desire. And that's typically how you would read a graph like this. And so we have different types, and the names kind of, I mean, if you go through a little bit with a little education here, right? Well, low pass filter, that would allow where it passes low frequencies, and then it would reject all high frequencies depending on what we set up as a high frequency. So when he says this here, like a low pass filter, see, passes all frequencies from zero to the cutoff frequency, and it'll block all frequencies above that frequency. And that's typically a low pass filter, right? So an ideal low pass filter, yes, has zero attenuation in the pass band, but in the real world, you're never going to have the ideal model. You're going to have what is close enough. So that's typically how to do it. So on paper, we would say, yes, it has zero attenuation, meaning that the signal is completely damped out and there's nothing to interfere with us. But ideally, the real world, you're always going to have a little bit of trickle in there, but it's such a low magnitude that it's not going to interfere with us. And this would be a typical graph response. We always look at like the voltage in comparison to the frequency as far as the voltage magnitude is concerned. So in this case, like in this, we have what they would call a high pass filter, the opposite of the low pass, right? In this one, we would reject all low frequencies underneath our cutoff frequency and allow all high frequencies to go through. And like I say, this is, again, it's another manipulation where we actually won't have any like new rules per se. We're still dealing with capacitive reactance and we're still dealing with inductive reactances as far as the formulas are concerned. It's just how we do it. So in a case like this, we would set it up like with a frequency in mind and develop our circuit that way. And again, just like how we did in resonance, I mean, in there we wanted a specific type of reaction and we chose, and we even seen that we can pick a few different components to achieve the same end. But they had something with the Q response, if you recall. And we could have a high Q or a low Q. And that we've seen both in the homeworks and in the labs. The labs we did have, right, where we had to change out the components and look at the high Q points and low Q points and see how those respond. So we're still dealing with that as far as this is concerned. But now we have a specific aim in mind where we want this. We don't just want to set it up for a zero response where we're just going for this one frequency, if you will. This one we're actually going for like a multitude of frequencies. And the two most common, it's like the low pass style and the high pass style. There are 5 altogether. And I might make a little table for you guys just to have as a sheet to use for reference for when you go on further into solid state. That would be like a little guide, if you will. Now here we have something that they call a bandpass filter. And what that does, if you notice the way the graph is, see here we set up 2 frequencies. And basically anything between those 2 frequencies is allowed, and anything under or over are those frequencies would be rejected. And again, remember now, this is just not communications where I mean like media communications, audio or video, if you will, where you have different type of signal transmission, but it also applies to power transmission, because in power, you don't want like noise spikes of different frequency, because that can interfere with machinery, your power cabinets and whatnot, what they're expected to see. So we don't want to be blowing fuses where we don't need to be. And so what they have is specific engineers like Ameren and whatnot would come out and actually install these circuits. And believe it or not, these are done for many like warehouses and factories and such, where they do actually install filters depending, on your machinery setup within your building. And you're getting like a specific kind of feedback, from different motors and whatnot being all coupled together. And so what they do is they go out and match that. And then if you were receiving like certain, let's say, noise spikes, okay, what they would do is actually set up a specific filter to reject those noise spikes, so you have good, clean signals coming in as far as transmission is concerned. And then we see another type, which is like almost like the opposite. See, if we look at the graph for the band pass rate, we go for a middle response here. Now the band stop is almost, and then one way to look at it is like in the reverse of that, okay? Where we are rejecting frequencies from frequency 1 to frequency 2 and allowing anything under or over to go through. And it's just different styles depending on what we're trying to achieve. In this case, let's say we are trying to get rid of a specific noise thing that's repetitive. We could go with a band stop and simply not allow that frequency to come through at all on our transmission. And then after that, there is one other, which is an interesting one. And you would almost have to ask, what would be the purpose of this? And I will show you. So then we get to the very last one where it's called an all pass. Now this one, yes, just as the name suggests, you are allowing all frequencies to go through. Now, what the heck would be the purpose of that? Well, I'm glad you asked. No. Um, for a case like this, like an ideal all pass, what happens with a circuit such as this, what you're doing is signal replication, where you're not allowing the original signal to actually go through. What you're going to do is replicate that signal. And what that does, believe it or not, it actually allows you to get rid of certain like noise ripples and such. So let's say you're producing a sine wave, and periodically, just for whatever reason, there's so many different reasons that could be happening. Who knows? Something's too nearby or something. The nuclear plant over there is interfering, getting different oscillations coming in from time to time or something like that. And then we would do a signal replication where we don't allow the original signal to come through, but we replicate it or duplicate it. And if you had periodic spikes coming through that aren't repetitive, let's say, then this thing will not reproduce those. It'll just reproduce the signal that comes through and is repetitive. And that's pretty much, that's the 5 types of filters that are available. And so depending on the situation, you would go ahead and select these types, of filters and set that up and then select your components based on your selection. So see here, he says, even though the all pass circuit has 0 attenuation for all signals, it's not going to dampen anything at all, but it's still considered a filter. We still ideally have an RLC type setup. And the thing is with these, they can be in a series configuration, they can be in a parallel configuration, and they can be in a series parallel configuration as well. And you'll find that depending on what we're trying to achieve is what dictates what selection we will make. I do. And so here, just like a general for all types of filters. And again, we're still dealing with, it's still just our, resistors, inductors, and capacitors. We're not adding any new rules per se at this point. At this point, we pretty much have exhausted all the rules that we're going to be applying. And now we're actually just doing something with it. It's like, okay, what's the point of all, learning all of these things? Well, we do use these commonly. And if you go ahead and look, even like on like a simple DC power supply, let's say you have a 24-volt DC power supply where you have 120-volt AC signal coming into it and you're pumping out a 24-volt DC. Well, if you were to open that thing up and look, you'll find right in the beginning there where we're receiving the AC signal, you'll find a whole series of capacitors, resistors, and possibly inductors in there. And these are set up to filter. So depending on how the engineer set it up, there might be a couple of different filters in there where maybe you have an all pass, or you're just doing a signal replication to clean it up. You might be getting, there might be a specific type of frequency that would interfere with the DC power supply. So you would set up a filter for that to block anything coming through and get nice clean signals. Ideally, that's what the filter's purpose is to give us nice clean signals to manipulate for whatever end we're going for. If it's audio in the case of like radio, or media transmission these days like MP3s and whatnot, even that, or video, and even in the case of the microwave transmission, even though it's ultra high frequency, it's still frequency transmission, and you can set up these filters for that. And again, it's just, it would be component selection based upon what you're trying to achieve. And a lot of times you can even go in online and they'll have these circuits already set up, and you would just go in and type in, well, I have this and this, and I'm looking for this. And ideally it would just create these circuits for you. You would have them set up and you could just go ahead and plug and play and use that. And then it would just be a matter of doing component selection as far as like, how much power you're expecting. If it's low power, you're just going to have little guys. But if it's big power, you're going to have some fairly large components that can handle that, right? So that's really ideally what this whole chapter is about filters, how to go ahead and select them, depending on what we're trying to do, and examining those. So he goes through and looks at the different low pass filters, and we'll look at circuit C. So these are all low pass filters, different configurations depending on what we're trying to achieve. And more commonly, you'll see down here, he uses a word called a choke. And a choke is that. And there are a few types of chokes that could be out there. And it means exactly as you think, right? It's choking. So what we're doing is trying to get rid of an unwanted signal or choke it out of the original signal transmission. So these types, we have low pass filters, depending on what we're trying to achieve. I mean, you notice we all have like a resistive load out there, depending on whatever it may be. And then we'll have different types that we can set up. In one case, like A, we have an RC type going on. And then, but look in B, we have an inductive type. And then C, we have basically all three, where we have an inductor, capacitor, and a resistor. But all of these will achieve what we wish. It's how they achieve it. Now, we know, all right, if we looked at it from a power point of view, the series is going to do one thing and the parallel is going to do something else. So that would be the ideal type thing that would dictate what circuit we would pick on what kind of power we would expect. And when I say power, I'm talking about what kind of current we were expecting. So now if we're going to go with like a low current, if you will, in a case of like a communications type thing, where we're dealing with radio signals or even television signals and that type of thing, the power is not very high. So we can go with like a low power type circuit where we're dealing with milliamps. But then on the other side of the coin, if we were to go with something like a power transmission, if you will, right? Let's say we're going with the outside lines or something like that, right? Then we would expect some very high type of currents to be happening there, where we're not really dealing in milliamps, we're dealing in straight amps. And then that type would dictate what kind of circuit we would select instead. But all of these are low pass filters. And you'll find as we go through filters, they do different responses. Now, one thing that I did want to introduce to you guys is something called a Bode plot. Now, this is something that will come up in your future. We're not going to do that here because the magnitude of it's a little much, and we're not going to have time to be playing around with Bode plots or dealing with circuits that have this type of response for us. So this is something that you will be dealing with when you get into in your beginning solid state class, is dealing with a Bode plots for your circuits. And what that does, now the one type of circuit we were looking at where we had the frequency responses, and then we had fallout on the one side and fallout on, fallout on the high side and fallout on the low side, right? What this does, the Bode plot is a different type of graph that shows us that frequency response and the range that's allowed there. Oh, let me go through here. And then, yeah, looking at high pass filters again. In this case, we're looking at frequency response. If we look at this first graph, and notice that it's saying we have a cutoff frequency of 50 hertz here. So that means if we look at this curve, that is our overall response for this circuit, okay? And once it hits this 50 hertz and plateaus there, that means that all of that is usable, right? And anything under that is unusable because this is the voltage. So as we go down and we start approaching zero here, that's our unideal area. Over here is where the voltage plateaus, and that would be our usable range because that's allowing our full voltage magnitude to come through. And that's how you would look at a plot such as that. We're just looking at overall frequency response in comparison again to what our voltage magnitude is. And again, notice, I mean, all of these circuits are considered high pass circuits. high pass filters in different configurations. The very first one is probably the most common and simple one where you have a simple RC circuit. It's not ideal. I mean, it can be a little flaky, if you will, in its response, but for simple, like low power circuits and whatnot, this would work. It would be cheap, and the more components, of course, we add, the drives up the expense of the overall circuit, if you will. And that's really, I mean, we're gonna look at. I mean, they have RC low pass, RL low pass, and ideally, it just really depends on what we're trying to achieve overall. And again, like I say, we're not really going to be playing with this. It's just more of an introduction, something that to look forward to in solid state, where you'll be playing with these types of circuits. And we have different formulas where they go through, and actually we introduce this new concept where it's the decibel. Now you may have heard of this, the decibel. They like to use it with sound, if you will, but more ideally, it's not just applicable to sound, it's also applicable to how we're looking at these frequency responses overall. But of course, sound waves do come through as frequency, so the decibel as an expression of how your power is acceptable. If you notice here that the formula, and we're not going to get into this, so don't get crazy, but notice that what the ratio is, they're using power, okay, the power out and compare it to power in, and we take what they call a logarithm, all right, and you wouldn't actually go through this like a mathematical formula. You would have like a log table, and you could go ahead and look these up. Your calculators do logs right on the fly and whatnot. So you would basically be looking at, okay, what's my overall response? And what it will do is it'll show you a range. And then how we look at that, yeah, here we go, is on what they call a log paper. And log graphs are strange. If you notice, see how it's like greater and then it becomes more condensed as it goes along. And that's basically to express how we're viewing these responses, if you will. And notice that it does say decibels and frequency. So we're looking at our ranges, like what could this circuit handle and overall, and what can we expect out as far as like a power type thing. So we would examine the decibels, and we would say, so like in a low power type circuit, when you're dealing with like radio transmissions, your decibel response would be like kind of tight and low in relations to your frequency response. And then in something where you have power transmission, you would see a much larger type curve. But I'm not gonna get much into that. We can go through and plot it. You look at the different frequency responses, if you will, over time, and see how the circuit responds to that, and as far as like what our voltage magnitudes are that we're getting out and things like that. And that would be your typical like a Bode plot, if you will, where it's showing what your decibel response is with your frequency range. And that's enough. I'm not going to bore the hell out of you guys with this crap, but uh, but that's where this is headed. I mean, we have reached pretty much the end of what we can and can't do with with resistors. What these are called are passive components, where they really don't do anything per se until we have a signal. So they just sit and wait. And until a signal comes along, right, we apply voltage to it, and then something happens. And that's why they call it the reactance, because as the signal comes through, these components react to that. And depending on their values is how they're going to react. And that's ideally our takeaways from this, is to get familiar with these formulas and in how these components reacted and what we can expect from that. And this just steps it further. And then what they do, like in the case of solid state, the next step, right, that is called active componentry, because solid state's a little different, as you'll find. They're nonlinear, and it's active componentry. And that's what you'll examine when you go into solid state. So again, I'll probably put together like a little review sheet for this, just as a takeaway for you, something to go with you for later. So if you do run into cases where you do need to look at RC circuits and whatnot, in any of your other classes and need to set something up like that, this would allow you to go ahead and do that. Our biggest thing was to get used to using these formulae and what we can expect to see. But that's really all I have. Like I say, this is going to be a slower week for us. We're really, really on track as far as what we wanted and everything. We've gotten our labs through. We've seen our combinations at this point, right? Series parallel and series parallel configurations and how we respond and what phases can happen. And at this point, um, we should be used to that, right? As we go low frequencies, more capacitive, higher frequencies, more inductive, and which way that's going to swing the curve, if you will. uh, but but that's really ideally what we have. So tomorrow when we meet for lab, I would like to hand out that speaker lab for us to go through. But then on Thursday, if you're all caught up at that point, you actually don't even have to come in on the Thursday lab. Again, like I say, we can use it for like a bit of review or catch up if you have a lab or two that you haven't finished or something like that, and you want to go over with me or just go over with the equipment and such. We can do that. Otherwise, yeah, Thursday can be a free day for you, and then and we'll probably review a little bit on Wednesday. I'll go over some topics, but it could be a short day, kind of like what we're going to do today. Um, and then Monday, I'll go ahead and like over the weekend, I'll put together a cheat sheet, if you will, just what topics we're going to cover in the final and what to expect. It's going to be 50 questions, just so you know, right? So 2 points a question, pretty much for as far as the grading end goes. So 50 questions on the homeworks that we've had. Okay. So it could be, and actually it could be homework questions or quiz questions, either one of those. And you should be able to go back and review all of your submitted ones. And if you can't, let me know, because that just means there's something goofy with the Blackboard permissions and I just got to go in and juggle something. But you should be able to pull up all your previous ones and use those as like study material. But yeah, I'll go through and actually put together a cheat sheet for you. And then the way I'm going to set that up for next week, it's not going to be definitely like one set day since we're going to be all at home and whatnot. And I know everybody's work schedules and such are always crazy. So I was thinking to go ahead and probably post the final on Tuesday and make it due on Friday. Friday, next Friday is like the absolute deadline for pretty much everything. I close my books on Friday. So if anything needs to be in, definitely for next week, we'll get that in and we'll see where everybody's at. But you should know where you're at. Blackboard, you can see what you have and don't have. And if you have any concerns, definitely reach out to me, over this week. And we will do what we need to do to get the job done. But that's really it. Like I say, at this point, I mean, really, we think about it, right? Looking at our formulas, and I mean, our two primary takeaways is really looking at inductive and capacitive reactance, or what our X of L is, what our X of C is, what we can do with it, that type of thing, and how we vary frequencies. And at this point, you guys have seemed done really well getting used to the lab equipment, dealing with the oscilloscopes and the waveform generators. And then basically from this point on, when you go into solid state and whatnot, you'll be using ideally all of the equipment on the bench then, because we use both DC and AC simultaneous when we deal with transistors, which you'll see when it comes up. But that's pretty much where we're headed. So, and I hope I get you guys for solid state. That's a fun class. But but that's really all I have for today. Like I say, we'll meet tomorrow. We'll do the speaker lab, and if you're all caught up with everything at that point, then really Thursday's lab can be a blow off day for you, where you don't have to come in, that type of thing. Otherwise, use it for a catch up day and we'll go with that. So, and there we are. That's it. That's what I got for you boys today. I hope you had a good Thanksgiving, a good week off. It was actually pretty nice, right? It looks like this week's going to be our cold one. But anybody have any questions on any of that, or we're pretty good?
All good.
Oh, you guys, don't
I
be.
think I'm all good, Tom.
Yeah.
Oh yeah.
All right. All right. I'll take your word for it. But like I say, yeah, if you have anything, going on, just shoot me an email. I try to respond quickly. More media, text me if you need to. But yeah, if not, I think everybody looks pretty good. And if you do have any concerns, like I say, definitely, reach out to me today, tomorrow in lab or whatnot, and we'll go over any concerns you have. But I think everybody looks pretty good, with all this craziness with the COVID crap and stuff, but we'll do what we do. As long as everybody's getting coursework in, that's my main concern, that you are familiar with those formulas and know somewhat how to juggle them, and that you can carry with you to all the rest of the classes that we have coming up, okay? But other than that, then I guess I will see you guys well, for those of you that can make it tomorrow, we'll see you tomorrow. Otherwise, we'll continue on as we are. All right, boys?
All right.
All right.
Oh yeah, I had a question.
Okay.
So you're talking about the homework. Were you talking about the homework you assigned over Thanksgiving, or did you assign new homework?
Nope, no new homework. My homework over Thanksgiving. That was
Okay,
our last big chapter.
just making sure.
Oh yeah, no, because I mean it goes hand in hand with like the last couple of labs, right, with the resonance and everything, and that was my ideal thing. I mean, really, our more focus is the stuff prior to that, getting used to the formulas and everything. So, and I think at this point everybody's done a pretty good job with that. So yeah, I don't want to push too much, too much more, because we really don't have, the time allowed. I'd rather focus more on getting these labs done and doing that speaker lab, and then studying for the final, so everybody does well. You know what I mean? But otherwise, I think we've done all the AC topics that we can have. Sound good?
Yep.
Yep.
Sounds great. I'll see you tomorrow.
All right. You guys,
Yep.
See ya.
See you tomorrow, Tom.
you guys have a good one.
See you tomorrow, Tom.
All right, Eli.